Black holes, one of the greatest mysteries of our universe. Invisible, unstoppable, and unbelievably powerful. These cosmic monsters have fascinated scientists and terrified storytellers for decades. The first black hole ever discovered was Cygnus X1, detected in 1964 by a team of scientists using X-ray astronomy. Since then, we've uncovered countless others, some so massive they defy logic. We're talking about black holes billions of times the mass of our Sun, lurking at the hearts of galaxies, including our own. In this video, we're diving deep into the true scale of these astronomical giants, from stellar mass black holes to the unimaginably massive colossi like TON 618. This is the real size of the universe's most terrifying phenomena. Welcome to the realm of supermassive black holes. But before we dive right into the scale, let's take a step back and understand what we're really dealing with. What is a black hole? At its core, it's not an object, but a region in space where gravity is so intense, nothing can escape. Not planets, not stars, not even light. Black holes are born when massive stars collapse under their own gravity. All that matter crushed into an infinitely dense point called a singularity, surrounded by a boundary known as the event horizon. Once anything crosses this boundary, it's gone, forever. But it's not just gravity that makes black holes terrifying. They don't just pull, they warp. They bend the very fabric of space and time. Near a black hole, time slows down, clocks tick slower, and reality itself becomes distorted. Fall too close, and time could stretch infinitely, as if the universe itself freezes around you. It's not science fiction, it's Einstein's theory of general relativity in action. And the more massive the black hole, the stronger this distortion becomes. To put things into perspective, even the smallest black hole ever discovered is still more massive than our Sun. Meet the Unicorn, the lightest known black hole, discovered in 2019. It sits quietly about 1,500 light-years away from Earth and has a mass 3 times that of our Sun. But here's the mind-bending part. All that mass is crammed into a sphere just 20 kilometers wide. That's smaller than the length of New York City. Think about it. Our Sun is over 1.3 million kilometers in diameter, yet this tiny object, just 20 kilometers across, holds 3 times the Sun's mass. That's the power of a black hole's gravity. It crushes matter to extremes we can barely comprehend. And remember, this is the smallest one we've ever found. Almost every galaxy we know of, including our own Milky Way, has a black hole at its center. Ours is called Sagittarius, a star, a supermassive black hole with a mass over 4 million times that of the Sun. And it's just sitting there, quietly lurking at the heart of the Milky Way. But that leads to one of the biggest misconceptions out there. A lot of people believe that black holes act like cosmic anchors, holding galaxies together, keeping stars in place. But that's not true. Black holes don't stabilize galaxies. They're not the glue keeping everything spinning in perfect motion. In fact, if Sagittarius A star suddenly vanished, the Milky Way would still remain mostly intact. Because as massive as our central black hole is, it makes up only a tiny fraction of the galaxy's total mass. The real force binding the Milky Way is the combined gravity of billions of stars, clouds of gas, and a whole lot of dark matter, the invisible scaffolding of the universe. Black holes may be dramatic, but when it comes to holding galaxies together, they're just one piece of a much bigger puzzle. When we talk about black holes, we're not just referring to a single type. There are actually several categories, each classified by its mass and size. The most common are stellar mass black holes, formed when massive stars exhaust their fuel and collapse under their own gravity. These typically range from about 3 to 20 times the mass of our Sun and span just a few kilometers in diameter. Despite their small size, they are unimaginably dense. Next, we have intermediate mass black holes, which are much rarer and more mysterious. Their masses fall between hundreds to thousands of times that of the Sun. Scientists believe they may form from the merging of multiple stellar mass black holes or within dense star clusters, but concrete evidence about their formation and location remains elusive. At the top of the scale are supermassive black holes, the true giants of the cosmos. Found at the centers of galaxies, including our own Milky Way, these behemoths can have masses ranging from millions to billions of suns. One of the most extreme examples is TON 618, which boasts a mass over 66 billion times that of the Sun. The exact process behind their formation is still unknown, but their existence is undeniable, and they are truly cosmic monsters. With all that in mind, let's begin the journey to understand the true scale of black holes. We'll start with stellar black holes, which are the smallest known black holes. But even within this category, black holes can get seriously big. One standout is LB1, located about 13,800 light-years away. It was once believed to be 70 solar masses, though later estimates put it closer to 23 times the mass of our Sun. Still, imagine 23 suns crushed into a sphere smaller than New York. Now step up to the next class, intermediate mass black holes. These are rare and mysterious. One candidate, GCIRS-13e, it was found just 26,000 light-years from Earth, near the galactic center, and is estimated to have a mass of around 1,300 suns. That's like taking all the stars you can see in a clear night sky and collapsing them into a point. The biggest intermediate mass black hole is HLX-1, located roughly 290 million light-years away in the galaxy ESO 243. This beast weighs in at about 20,000 solar masses. That's nearly 5,000 times heavier than the unicorn, and still just the middle tier of black holes. Now we've reached the giants, supermassive black holes. Even the smallest known supermassive black hole discovered so far is still astonishing in its scale. Located in a dwarf galaxy called RGG 118, this giant has a mass of about 50,000 times that of our Sun. Despite being relatively light for a supermassive, RGG 118 still possesses the power to shape its entire galaxy, proving that even the smallest in this class is anything but insignificant. But in our own cosmic backyard, there is a monster, Sagittarius A. The supermassive black hole at the center of our Milky Way is about 26,000 light-years away. It has a mass of roughly 4.3 million suns. Its event horizon spans 44 million kilometers, about 30 times the diameter of the Sun. If you replace the Sun with Sagittarius A, Mercury would orbit inside the black hole. Yet, Sagittarius A is tiny compared to what's out there. Let's head 53 million light-years away to the galaxy Messier 87, where the first black hole image was captured in 2019. M87 is a true monster, weighing around 6.5 billion suns. That's more than 1,500 times the mass of Sagittarius A, and large enough that its event horizon would stretch beyond the orbit of Pluto. Place it where our Sun is, and the entire solar system would vanish inside. But even M87 isn't the end of the road. And then we reach the final boss, TON 618. Located a staggering 10.4 billion light-years away, TON 618 is one of the most massive black holes ever discovered, weighing in at over 66 billion solar masses. Its event horizon spans 390 billion kilometers, enough to engulf the entire solar system, the Kuiper belt, the Oort cloud, and keep going. Discovered through the light of a hyperluminous quasar it powers, TON 618 continues to baffle scientists. It's a cosmic anomaly that pushes the limits of what we thought was possible. From stellar black holes to supermassive giants, we've seen how mind-bogglingly massive these cosmic beasts can be. In the vastness of space, black holes are the true kings, and we've only just begun to understand their power. What if the universe had a place where time flows backward, where nothing can enter, but everything must leave? You've heard of black holes, cosmic monsters that consume everything. But hidden within the math of the universe, there's something even stranger, something we've never seen, but might explain how the universe began. This is the white hole. White holes are theoretical objects predicted by Einstein's general relativity. Imagine a star, but instead of collapsing under its own weight, it does the reverse. It explodes endlessly. It doesn't suck in light. It throws it out. It doesn't trap time. It repels it. You could fly toward it, but you'd never reach it. Its gravity wouldn't pull you in. It would violently push you away. Physicists discovered white holes while studying the mathematics of black holes. They weren't looking for something new. They were trying to understand how a black hole forms and what lies at its center. But buried deep in Einstein's equations, they found something strange, a mirror image, a mathematical twin of a black hole. And in the 1930s, Albert Einstein and physicist Nathan Rosen explored this idea further. They proposed what's now called the Einstein-Rosen bridge, a shortcut through space-time that connects two distant points. In theory, the entrance of this bridge is a black hole. But what about the exit? You fall in and you fall out, but not in the same place, maybe not even in the same universe. For decades, they remained purely theoretical, a whisper of symmetry in the universe. But as our understanding of black holes grew, the mystery of their opposites only deepened. No one has ever observed a white hole, and there's a good reason. White holes might be highly unstable. Even the smallest disturbance, like a dust particle trying to enter, could collapse it. Also, many scientists believe they might have only existed in the early universe, shortly after the Big Bang. But that's only half the story. Some physicists propose a bold idea. The Big Bang itself was a white hole. Think about it. An object that ejects infinite energy and matter in an instant, creating space and time. Sound familiar? In fact, some versions of loop quantum gravity suggest that black holes don't end in singularities. Instead, they bounce into white holes. This bounce could be how new universes are born. There is another theory by physicists Carlo Rovelli and Francesca Vidotto. They proposed that white holes might not just be early universe relics. Instead, they could be the final stage of a black hole's life. After a black hole slowly evaporates through Hawking radiation, it could rebound and release all its energy as a tiny white hole. This process could take trillions of years. In this theory, black holes don't just disappear, they transform. Every black hole might one day become a white hole, exploding into light at the end of time. If white holes really are the final echo of a dying black hole, then they're not just ancient relics. They're flickering embers of the cosmos, waiting for their moment to awaken. But spotting one, that's the hard part. They'd be small, silent, and almost impossible to detect until they erupt. Still, some researchers believe that the universe may have already whispered clues to us. Mysterious phenomena like certain gamma-ray bursts or fast radio signals, sudden unexplained flashes of energy, might be the birth cry of a white hole finally igniting. Others suggest primordial white holes, formed in the earliest seconds of the universe, could still be drifting through space, untouched and invisible, until they explode. And if we ever find one, it wouldn't just be a discovery, it would be a revolution in how we understand space, time, and even the fate of reality itself. Now, many of you would have a question. What would happen if someone tried to enter a white hole? The short answer: you can't. Unlike a black hole, which pulls in everything, light, matter, even time, a white hole does the opposite. It repels everything. Its event horizon isn't a doorway, it's a wall. Nothing can go in, not even information. So the idea of falling into a white hole isn't just dangerous, it's physically impossible. White holes challenge our understanding of reality. They twist time, reverse gravity, and might hold the key to the multiverse. Right now, they live only in equations. But so did black holes once. And then, we saw one. So maybe, somewhere out there, beyond the reach of our telescopes, a white hole is already exploding. Somewhere in the silent depths of the Sagittarius constellation, a giant is dying. Not peacefully, but violently. This isn't just another fading star in the night sky. It's a volatile and unstable cosmic monster. A star so aggressive that it's been tearing itself apart for thousands of years. Its surface burns hotter than nearly anything we've observed in the universe. Its winds blast matter into space at millions of kilometers per hour. And deep within, pressure is building. And the terrifying thing is that it appears to be aimed directly at us, pointed like a loaded cannon across the galaxy, spinning, waiting, ready to release something far more devastating than any supernova. A gamma-ray burst, the most powerful explosion in the universe. One that wouldn't just light up the sky, it could erase entire atmospheres. If it fires, we won't see it. We won't hear it. We'll simply cease to exist. This is WR104, the most dangerous star we've ever discovered. And it may be the single greatest existential threat humanity has never heard of. This gigantic star is not an ordinary star. It's part of an elite, terrifying class of cosmic titans known as Wolf-Rayet stars, a name that sounds mythical, and for good reason. These stars are rare, extremely rare. Less than 0.1% of all stars ever reach this stage. Because to become a Wolf-Rayet, a star must first be enormous, at least 25 times the mass of the Sun. And then, it must begin to die in the most violent way imaginable. Picture a furnace so hot, it melts not metal, but atoms. These stars burn at temperatures exceeding 200,000 degrees Celsius, fusing heavier and heavier elements in a desperate race against time. As it collapses inward, its outer layers are blasted off into space, not slowly, but as if fired from a cannon, at speeds approaching millions of kilometers per hour. These high-speed stellar winds carry away enormous amounts of mass, forming spiraling shock waves of gas, dust, and radiation. A cosmic hurricane so powerful, it reshapes the very fabric of the surrounding space. In fact, WR104 has already lost more than half of its original mass. Not over billions of years like normal stars, but in a cosmic blink, just a few 100,000 years. What's left behind is the unstable, superheated core of a dying beast, a spinning, radioactive engine of destruction, and it's spinning fast. Because it's what could focus the energy of its final explosion into a narrow, lethal beam. A beam so precise, so intense, that it could stretch across light years and still shred anything in its path. When this titan dies, it would die in the most violent way known to science. Through a gamma-ray burst. Gamma-ray bursts are the universe's most powerful explosions. They are not like the fiery blasts of supernova we've seen in telescopes. They are something else entirely, a focused beam of pure energy, forged in the final seconds of a star's collapse, narrower than a laser, yet more destructive than a billion nuclear bombs detonating at once. In just a few seconds, a gamma-ray burst can release more energy than our sun will emit in its entire 10 billion-year lifetime. That's not an exaggeration, that's astrophysical fact. And if that beam happens to be pointed directly at Earth, we won't even see it coming. The gamma rays travel at the speed of light. And even today, with all our satellites, we can only detect a gamma ray burst after it begins. There's no early warning system, no global defense plan. If it comes, we learn about it after it has already struck. Scientists believe a gamma-ray burst may have hit Earth around 450 million years ago, triggering the Ordovician mass extinction, which wiped out over 70% of marine species. No crater, no asteroid, just radiation. From a star we never saw. And if it has to happen again, then it would be cruel. In 1 second, Earth's upper atmosphere begins to ionize. High-energy gamma rays tear through the ionosphere, stripping electrons from atoms. A chain reaction of electrical disruption begins. Satellites flicker and fail. Communication links drop. GPS, weather monitoring, and communication systems start to break apart. Silently, invisibly, without a single warning light to the people below. In 5 seconds, the ozone layer is obliterated. Not weakened, not damaged, just gone. Vaporized by the relentless energy of the gamma-ray burst, leaving our planet fully exposed to the sun's ultraviolet radiation. UVC rays, normally filtered out completely, now reach the ground. Within moments, sunlight itself becomes hostile. Life beneath the sky becomes vulnerable. Skin burns faster. DNA begins to mutate, and the planet is no longer protected from what's always been above us. 5 minutes after the impact, crops begin to show signs of stress. Leaves curl, dry at the edges, and lose color under the punishing light. Insects vanish. Bees abandon their hives. In 1 hour, the oceans begin absorbing the damage. The surface, once a shield of life, becomes a target. Ultraviolet radiation penetrates shallow waters, reaching depths it was never meant to touch. The first victims are the smallest, phytoplankton, microscopic, invisible, but essential. As they die, the very base of the marine food chain begins to collapse. Oxygen production, nearly half of what every living being breathes, is thrown into uncertainty. Coral reefs grow pale. Fish populations scatter, disoriented by the sudden change. In 1 year, global food systems collapse. Famine spreads, quietly at first, then violently. Supply chains fail. Crops don't grow. Oceans offer nothing. Weather patterns spiral into chaos. Seasons lose meaning. Droughts, floods, and storms arrive without warning and without end. Ecosystems crumble, species vanish, not one by one, but in waves. What begins in the oceans spreads to the forests, the plains, and the skies. A global mass extinction takes hold, and Earth is no longer Earth as we knew it. And it all began with a beam of energy from a star 7,500 light-years away. WR104 reminds us, in a universe this vast, even silence can be deadly. Are we inside of a black hole? As mysterious as our universe is, this theory gives a new perspective towards the universe and the reality itself. Let's break it down. A black hole forms when a massive star reaches the end of its life. Its core collapses under the force of its own gravity, so powerfully that it creates a region where the laws of physics begin to break down. The edge of this region is called the event horizon, a boundary beyond which nothing can escape, not even light. Once you cross it, you're no longer part of the universe outside. You're falling inward forever. Our universe, the one we live in, also seems to have its own cosmic horizon, a boundary beyond which light can't reach us. Not because of gravity, but because of how fast space itself is expanding. Just like a black hole's event horizon, once something crosses that boundary, it's gone, forever cut off from view. If you calculate the total mass of our universe and compare it to the mass of a black hole, which would need to match its size, you get something shocking. They're almost the same. A universe the size of ours, with the mass we observe, would fit the characteristics of a black hole, if seen from the outside. This isn't just poetic coincidence, it's mathematical alignment. Let's make it simpler for you. Our universe is about 93 billion light-years wide and contains an estimated mass of roughly 10 to the power of 53 kilograms. That's a 1, followed by 53 zeros. If you were to create a black hole as large as the observable universe, it would need to have almost exactly that much mass. In other words, if the universe were a black hole, it would look just like this from the outside. Same size, same mass, same horizon. So what if it's not a coincidence? What if we're not just looking at the universe from within, but looking outward from deep inside a black hole? According to Einstein, a black hole isn't just a collapsed star. It's a distortion in space and time itself, so extreme that it bends reality into something new. And the equations of general relativity don't stop at the singularity. In fact, they suggest that beyond that singularity, there could be something else. A bridge, a tunnel, a doorway to another region of space-time. The theory suggests that our universe could be the inside of a black hole formed in another, far more massive universe. A universe we'll never see, but one that might exist on a scale beyond anything we can imagine. For them, we are microscopic, just a tiny bubble of space and time, barely a flicker in their unimaginable vastness. But for us, they are unreachable, a realm beyond our dimensions, beyond our physics, beyond even our ability to imagine. Our universe might just be one drop in an infinite ocean of realities, each one isolated, each one unaware of the others, each one born inside a black hole. Every black hole in our universe could be the seed of another universe, and every one of those universes might contain its own black holes and its own realities within them. Realities stacked within realities, dimensions inside dimensions. A multiverse, not spread out like parallel lines, but nested deep inside gravitational wells. But can we ever know for sure? Right now, There's no way to look beyond our cosmic horizon. No instrument can peer outside the universe to check if we're truly inside something else. And even if we were, the laws of physics as we know them wouldn't apply beyond that boundary. It's like trying to understand the ocean while trapped inside a single drop of water. Endless creation, inside endless destruction, worlds within worlds, and we are just one of them. So next time you look up at the night sky, remember, you might not be looking out into the universe. You might be looking deeper in.
Now, scientists have found the strongest evidence yet.
K2-18b.
Exactly 124 light-years away, in the Leo constellation, we might have found life. Not intelligent beings, not alien civilizations, but something just as groundbreaking, the chemical fingerprints of biology, on a planet that isn't Earth. This world is called K2-18b, and it may change what we thought we knew about life in the universe. K2-18b is almost 8.6 times bigger than Earth, and it orbits a red dwarf star named K2-18, a small and relatively cool star compared to our Sun. Yet despite this, K2-18b sits in what scientists call the habitable zone, the sweet spot around a star where temperatures could allow liquid water to exist. The planet lies within the Leo constellation, a region of the sky visible from Earth, and belongs to a solar system very different from our own. Its parent star, K2-18, emits far less light and energy than the Sun, but that actually works in the planet's favor, because K2-18b is located much closer to its star. This tight orbit keeps the planet warm enough to potentially support life, even without the bright sunlight, unlike Earth. It is classified as a Hycean planet, a new and rare type of exoplanet that could have a hydrogen-rich atmosphere and vast oceans beneath its surface. Around 1 year ago, NASA, using the powerful James Webb Space Telescope, made a discovery that would send shockwaves through the scientific community. They turned the telescope's ultra-sensitive instruments toward the exoplanet, not expecting much. It was larger, gassier, and strange. The telescope detected key chemical signatures in the planet's atmosphere, including carbon dioxide, methane, and traces of something far more intriguing, dimethyl sulfide, or DMS. Why is that so important? Because here on Earth, DMS is only produced by life, specifically by microscopic organisms in the ocean. This moment marked the first real evidence that an exoplanet outside our solar system might be harboring life. The lead researcher behind the discovery, Professor Niku Madhusudan from the University of Cambridge, said, "This is the first time we have detected possible biosignatures on a planet in the habitable zone." He went on to explain that K2-18b is not just another exoplanet. It's one of the best candidates we've ever found for hosting life. According to him, the detection of DMS was not expected, and if confirmed by future observations, it could change our understanding of life in the universe. As the planet is 8.6 times more massive than Earth, that means its gravity is significantly stronger, and it likely has a much thicker atmosphere made up of hydrogen, helium, methane, and other volatile gases. It's what scientists call a Hycean world, a type of planet that's somewhere between a super-Earth and a mini-Neptune. These worlds were once dismissed as too hostile for life, but now they might be the best places to look for it, because beneath that heavy, hazy atmosphere, there could be something astonishing: warm oceans, cloud layers rich in organic molecules, and maybe, just maybe, life. K2-18b offers more than a scientific mystery. It's a window into what's possible. If life can form there, in conditions so different from Earth, then maybe it's not rare. Maybe life is everywhere. But for now, the reality is that it's located 124 light-years away from Earth. That's over 1.17 quadrillion kilometers. So while we can study its atmosphere, detect its chemicals, and theorize about its oceans, we can't touch it. We can't visit it. Not yet. As of now, it remains a distant world, glowing faintly in the Leo constellation, a place we can observe, but not reach. A place that might be alive, but will remain a mystery for generations. This is the closest we've ever come to finding life beyond our world. And it might just be the beginning. That's all for today. See you in the next. Until then, stay curious and keep watching. That's how.